Bismillahirrahmanirrahim. Well, today we will cover experiment number 11. I just made the complete observation video separately that will be shared in your Google Drive. This video is regarding the theory explanation of this experiment. Well, this experiment is very interesting and amazing. You will find its application in next semester in CFPS, computational compressible flow and dynamics. And propulsion system, sorry, compressible flow and propulsion system. Okay, so well, it's related to rocket science, all the rocket science related to the converging diverging nozzle. So it's one of the experiment there in which we are experiencing the shock wave, the normal shock wave, oblique shock wave that occurred in the converging diverging nozzle. That very amazing phenomena occurred in the nozzles, and it is in all rocket propulsion system. All rocket propulsion system are capable of moving at more than supersonic velocity. So going towards supersonic velocity, there's a phenomena of inside the throat normal shock wave, then it moves towards at the exit and become oblique shock wave and have a converging and expansion fans. Anyway, now comes towards the experiment number 11. Well, this is first I'll show you the apparatus. This is the pressure gauges. This is the pressure gauges. This is the testing bench, in which in the center we have installed converging divergent nozzle in this center. This is the inlet chest where the steam is coming from the boiler, and this is the exhaust. Okay, full brief. This is the heat exchanger going of the nozzle, the cooling tower, heat exchanger with that converts steam into the water, and here we collect the condensed steam. This is the wheel in which a metal probe is rotating along the position of the nose. That already describes in the later video. Now come towards the our current experiment. This is the list of symbol that has been used in this derivation. Okay, we have 4 types of nozzles: converging divergent nozzle, convergent 3-degree divergent, it's less divergent than first one, then convergent and convergent parallel. Convergent only don't have a divergent section, so it will not go beyond to the supersonic velocity. Maximum it goes to the sonic velocity, and similar with the convergent parallel. Okay, here we have a multiple experiment, but we will cover only the performance of the nozzles. The investigation number 1, that is related to investigate the variation of the pressure along the nozzle profile for a series of back pressure and plot graph of pressure against distance. So this is the graph which we are going to observe or produce after getting observation readings. Okay, so now comes towards the basic just move towards the basic. This is basically inside of nozzle we have a converging section and then divergent section. Okay, so and we have a probe in between. No, I just make a picture from this is basically schematic of test bench of nozzle. Here we placed nozzle, that you can see that it is a convergent than divergent nozzle. Okay, and this is the metal probe. This metal probe is basically observing the pressure reading when probe is here, it records the reading at this point. When the probe is here, it's record the pressure at this point, and similarly at the later points. So when the steam coming over here, first the velocity is increased and pressure is decreased. Okay, so we are observing pressure. So as we are moving the probe, the pressure is decreasing, means so pressure is increasing means the velocity increasing. The pressure is inversely proportional to velocity. What does nozzle do? It converts pressure into velocity. So definitely here the pressure will be the pressure will decrease and the velocity will increase. But if the flow is not enough, if it not goes to the sonic velocity at the throat of the nozzle, then this divergent section work as a diffuser for a subsonic flow. So the pressure again rise. The pressure again rise and the velocity will decrease, because the diffuser will increase the pressure and decrease the velocity. So we have a number of reading that, and we have to set at which point the nozzle comes into its designed position. Because if the throat we don't have a sonic velocity, we don't have a increasing velocity after the exit of the nozzle, because the amount of we increase the velocity in the diffuser, thus the pressure rise and velocity decreases. So the first graph, it happens like that. If we now move towards this video. Yes.
Okay, and that's really not necessary.
Yes. Yes. This is the converging divergence. Okay. So we don't. This is basically graph which we are want to produce. This is the distance, the x distance. This is the pressure values. So consider that this wall is 100% closed. The steam in and the steam is not allowed to flow. So the pressure over here is equal to the pressure over here. So if we move the probe towards its x direction, the pressure will not increase or decrease. It's a linear. Will not zoom out. So the value will be exactly same. So now assume that if the supply pressure is fixed, because it's coming from the boiler, we can only open the valve from this point to allow to steam to flow, and further we decrease the discharge pressure by converting this steam into water, because when the steam convert into the water, it contracts and becomes water. So volume decrease, so the pressure over here will decrease. So the more pressure decrease over here, the more velocity of the steam will produce, the more steam will pass from this channel. Okay, now we are moving, now we are decreasing the now we are opening the valve and reducing the pressure. So the velocity will the pressure here goes like that. It will reduce like this. The pressure decreases as it is a converging nozzle for the subsonic flow, and at this point the throat the velocity is not sonic velocity. So the divergence section act as a diffuser. The velocity again decrease and the pressure rise. You see that graph? Similarly, we are open more valve. So we are basically what we are doing, decreasing the back pressure. We are decreasing the back pressure. So as we are decreasing the pressure, the velocity increase then decrease, increase then decrease. The pressure decrease then increase. Okay, you can relate this. But when we open at its designed position, like at this point, the flow is enough that velocity at the throat becomes sonic. Okay, it becomes sonic. So what happened, this region becomes, because before the sonic velocity, this region is subsonic, this region is subsonic but has a high velocity. You see that? and a low pressure, and this region is having a low velocity and high pressure. You see that. So we have two different medium. When it goes to the sonic velocity, due to the large difference, the air compress. Here you see that difference. This particle moving less, this particle moving with high velocity. So collapsed. It collapsed and produce normal shock wave. That's why you see that when the normal shock wave produces, it disrupts the flow, and it also decrease the velocity. So again the pressure rise. It will not becomes at the exit of nozzle. It's still we don't have a design condition like high velocity and the lowest possible pressure. So the pressure rises again. This normal shock wave then move towards the exit of the nozzle. That's a very amazing phenomenon have in the every converging divergent nozzle. So the sonic that's why it is always observed that when the flow becomes a sonic, you observe boom, sonic boom, called sonic boom. If the fighter plane moves in the air with the high when it goes into the sonic velocity, suddenly a shock boom producing. That is a natural phenomena. Okay, that is a normal shock wave that moves along in this direction. Let me show a simulation video of this. It's a very interesting phenomenon. And then when the whole shock wave move at the exit of the velocity, then it's open area, then the shock wave become oblique. Then we have a convergent and expansion fans that will be discussed in your next semester in CFPS. Okay, now let me close this and show you. To show off, this is the oblique shock wave. First, we have to show. Yes, in this picture, I just in order to save time, I just move. Yes. Now you see that this is the divergence section. You see that as the flow is increasing, this is the low velocity region, this is the high velocity region. So between them we have a normal shock wave, and it moves in this direction as we decreasing the discharge pressure. Because supply pressure is fixed, it is 8 bar from the steam, we can only decrease the discharge pressure. So as the flow is this normal shock wave move towards at the exit of the nozzle, and after getting at the exit of the nozzle, you see that every rock propulsion, whether it's a rocket for going to towards the space, you see that converging divergent nozzle, and we have a lines of normal shock wave. Let me show you in this video. Yes, and after passing out of the nozzle, this shock wave becomes oblique. Before the enclosed path, we have a straight line, some like curved line, but when it goes to the open surface, it becomes shock wave. And after shock wave, we have a conversion and expansion fan. When that is also phenomena, it will be discussed in your later semester. Well, in the similar, we are observing these shock waves in this graph. Okay, with our experiment is that we are observing the disruption lines when we are going from sonic velocity to supersonic velocity, subsonic to supersonic velocity. Okay, let's move towards our experiment. Just last video that I found very interesting in the internet. Also, this is the simulation video. Let me show the real video of the show. This is the nozzle. This is the another type of nozzle that we'll discuss in the later. You see that the sudden sonic boom producing, and these are the convergent expansion one. This is, we also don't want very large convection expansion fan, because it also reduces the velocity and decreases the efficiency of the nozzle. So the ideal condition that we have after discharging the fluid, we have we have to have same pressure at atmospheric pressure. Okay, now move towards our experiment. In our experiment, we first set this is P3 pressure, this is P2 pressure. This pressure is coming from the boiler. It's around 7 8, it's up to up what pressure we set over here. And as we are opening this valve, the pressure in this chest pressure will decrease. Okay, and this is the nozzle pressure that moves along this direction. So now comes toward the uh, graph which we are intends to. These are the profile of the nozzle that already we are currently doing experiment with this nozzle, converging, divergent, 3-degree inclined. This is the actual graph of the converging, divergent motion, 3-degree. So this is the inlet pressure, this is the chest pressure. Okay, this line represent, first we reduce the pressure, but the velocity increase, the pressure decrease, and again pressure rise. It will not come to the direction. Then suddenly we have this, and after reaching this, that you have very abduction formula. This sudden pressure rise, decrease, and disturbance is due to the normal shock wave, and it moves along the path. Okay, as we are decreasing the pressure, this shock wave is moving till the exit of the nozzle. This is the position of the nozzle basically. Minus test in initial, at 0 we have throat, and after 0 we have after this point, sorry, we have a divergent section. So you can see that for the series of the pressure drop, we get to the design position. You can also find out at which pressure it will work as per design condition or most efficient by simple this derivation that already had done in your workbook. It goes, yes, these are the long derivation. I don't want to get to this derivation. Now comes to direct conclusion of this derivation, that is, this is it. The following approximate value for N, and N is the superheated steam. For N superheated is 1.3, initial dry saturated steam 1.13, and initially wet steam 1.113. So currently we have an initially dry steam, saturated, not superheated steam, because we don't have a superheater. So we just take and 1.13. This is the basically the discharge pressure, and this is the supply pressure. So let me assume that if the supply pressure is 8 bar as per our boiler, if we multiply by with 0.57 0.578 basically this 0.7 where we get this 0.578 by this derivation. P2 is equal to P1 multiplied by 2 divided by N. We set N 1.13, then we get the equation P2 is equal to 0.578. So if we multiply by 8 with 0.578, we get the value of 4.62. So if we set the discharge pressure around 4.62, we get the design condition. And after reducing further pressure, we don't have increase in velocity, because at the throat we have a maximum sonic velocity is equal to, we have a maximum velocity that is equal to speed of sound. So after reducing pressure from 4.62, the velocity will not increase. Similarly, the flow will not increase. So this is called a choke flow condition. Okay, and this graph represent the choke flow. Okay, as we are this is the flow, mass flow rate. As we are basically P2 or P1 is fixed 8 bar, P2 is decreasing as we are opening the wall. You can see that the mass flow rate is increased as the wall is opening till this point, and after reaching this is design condition like 4.62, the mass flow rate becomes constant. This is the choke condition. This application is used in multiple engineering. This phenomena has a multiple application in engineering machines, like your carburetor. We also have a choke condition, that after that the mass flow rate will not increase, because if increased it has an adverse effect in the engine. Similarly, every nozzle have this choking condition, because at the throat we have maximum velocity of sonic velocity, speed of sound. We cannot increase the velocity more than sonic, so we have a at this thickness of the throat, not maximum after reaching the maximum mass flow rate, the mass flow rate will not increase. Okay, so because at throat we cannot increase velocity more than sonic velocity, so this is the choke flow condition. Okay, here we have to draw this graph, not this line, because we said at design condition. Okay, at lower pressure more than 4.62, so we have a graph like this. The actual graph, uh, let me show you the actual graph. After that we have observation video. You just make a graph from those observation videos. Okay, these are the reading. This is position point -10, -8, -6. We are moving along the no distance. The pressure is what? The pressure reading will decrease and the velocity increase, because the initial pressure is 7.5. You can see that the steam inlet pressure is 8.2. At chest pressure, bar pressure, we said pressure is 7, around 7, and the exhaust pressure is 1. Usually it is less than 4.6 bar, so it works in the design condition. After exit of nozzle, we have a converging divergent fence that produces abduction in pressure. You see then the graph, but till the exit of the divergent section we have a smooth maximum velocity and smooth pressure reading. You can see the 7.5 decreasing to the 2.2 max and 1.8, and after that the pressure reading becomes constant. You see that point 1.7, 1.6. We have some variation in this, and the graph will, you just take this, make the graph. This is the in y direction we have pressure, in the x direction the distance of the nozzle, and as we moving the probe, the pressure is or around constant. When the convergence section start, the velocity increase, pressure decrease, and in the divergence is also decrease, and after that we have some abduction increase, decrease, body, something like that. Okay, so this is the end of the theory. I hope I'll explain everything regarding its theory. Let's after that we have a observation video. Take this observation reading, note in your workbook in this like this, and make a graph like this. In this experiment we don't have any calculation, something like that. Just we need to make the graph from these reading. Okay, this is you just draw this -8, -10, -10 to -8 to maximum 80 in x direction. Okay, and make dot 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 and just draw the line from the dot and make the graph. Okay, till then, Khuda Hafiz. Thank you for watching this video.